This is Gail Langevin with the Office of Strategic Communication and Education. Today is March 30th, 2007, and I'm speaking with Doug Dwoyer, Associate Director of Langley Research Center. Doug, when you began at NASA, what branch were you assigned to and what were your duties?
I was assigned to the Theoretical Aerodynamics branch. Jerry South was the branch head, and my duties were to develop computational fluid dynamics techniques for predicting transonic aerodynamics. And
tell me more about the development of computational fluid dynamics, or CFD codes.
Well, when I joined NASA in 1977, the name computational fluid dynamics, or CFD, had actually just begun to be used. It was before that, a number of people were experimenting with using numerical solutions of differential equations to predict fluid flows in academia and various government labs, but it was not really an organized discipline. And in the 1970s, it began to emerge as an organized discipline in mathematics and engineering. And Langley and NASA played a major role over the next 30 years in the maturation of CFD, particularly in its application for aerospace engineering. At the time that I joined NASA, most CFD techniques were focused on the numerical solution of linearized equations of motion for aerodynamics. These are approximate equations of motion that ignore certain key features of aerodynamic flows. For example, in a linearized model, you cannot predict shock waves. And then they were accompanied by numerical solutions of the boundary layer equations. As we went into the 1980s and the late 1970s, really, the focus began to shift to solving the true nonlinear equations of fluid mechanics first, remaining with the approximation of inviscid, or ignoring viscosity in the calculation for the majority of the flow, and then accounting for viscosity with boundary layer calculations. And then on into the 1990s, focus again began to shift to solving the full equations as they were known at the time of fluid mechanics, which are the Navier-Stokes equations, but amended to account for the effects of fluid mechanical turbulence in an approximate way as opposed to an exact way. So there was added to the Navier-Stokes equations the so-called turbulence models. So Langley, one of the key roles that developed at Langley was around the mathematics of the solution of all of these classes of equations, the linear equations, the nonlinear inviscid, and ultimately the Navier-Stokes equations. And a rather innovative way that Langley was able to do that was through an institute that was on the center at that time called ICASE. Had the original name of the Institute for Computer Applications in Science and Engineering, ultimately just officially shortened its name to ICASE because it was widely known by that acronym. That institute was established by Dr. John Duberg in 1972 when he was the then Associate Director of Langley Research Center, and he established it to take advantage of a unique opportunity at Langley, which was the acquisition of an early supercomputer called the Star 100. This was a vector supercomputer, the first of its kind. It was put on the market by Controlled Data Corporation, which now doesn't even exist anymore. So he wanted to provide a place where we could invite mathematicians and computer scientists to come work at Langley with our staff to take advantage of this new computer. So through ICASE, Langley established a vibrant program of visitors in the fields of computer science and mathematics, particularly the mathematics of numerical solution of differential equations. And there was a strong program of visitors every summer. There would be 30 to 40 mathematicians and computer sciences visit through iCase. And then during the course of the year, we would have faculty from around the world who would come in on their sabbaticals to work with our staff. That program continued for a good 20 years, and through it, many of the advances in computational fluid dynamics, especially those associated with compressible flow, were developed. So for example, we had visitors from Israel and Europe that helped us develop a class of numerical algorithms known as total variation diminishing methods that were attuned to capturing shock waves without excessive oscillations in their immediate vicinity in the computation. We worked a lot to try to understand the dissipative nature of numerical algorithms and how they affected the accuracy of solutions, and did a lot of work on proper specification of boundary conditions. And this initially started out for the nonlinear transonic potential flow, then went on to the Euler equations, and then ultimately to the Navier-Stokes equations. So that whole activity at iCase involved a collaboration between staff at Langley and these visitors from various universities worldwide. And the staff at Langley would take the theory that was developed by the iCase visitors and convert it or translate it into practical CFD codes that were tested and validated against experimental data that came out of Langley's wind tunnels. At the same time, another very powerful CFD program that was started in NASA at NASA Ames Research Center. And this was typical of NASA research in the 70s and early 80s, where headquarters deliberately set up competitions between the centers in order to accelerate progress in the field. So Ames also had a strong program, and there was a strong sense of rivalry between the Langley activity and the Ames activity. Ames was able to advocate for and acquire a program called the Numerical Aerodynamics Simulator in the 1980s, and through that program was able to have what was always the most powerful supercomputer of its day available to all NASA CFD research centers at Langley, then called Lewis Research Center, as well as at Ames Research Center. And we had a network connection to the NAS, and researchers at Langley were able to utilize that computer. And we always, through at least the early 1990s, were able to maintain our own supercomputer here at Langley as well. So following the Star 100, we got a CDC Cyber 203, followed by a CDC Cyber 205, and then ultimately a Cray 2, and followed by a Cray YMP, all here at Langley. And at Ames, they acquired a whole series of Cray supercomputers until ultimately Cray went out of the business, and they have been they still have the NAS operating at Ames that currently utilizes massively parallel systems that are based on microprocessor, large forms of microprocessors. So the Ames-Langley rivalry, I think, greatly accelerated a lot of the compressible flow technology, with Langley's approach generally tending to be more theoretical sound and mathematically sound, and Ames program trying to go out there and just make the most advanced calculation that possibly could be made using the big Cray computers that were installed out there. I think one final comment to make is that some of the, that at Langley, when I arrived, there was really only one branch focused on CFD totally, and that was the theoretical aerodynamics branch that I joined in 1977. By the early 80s, there were two more CFD branches established, one focused on subsonic flows and one focused on supersonic flows. And I was selected as the first branch head of the supersonic branch. That was the computational aerodynamics branch. And it was complemented by a subsonic computational aerodynamics branch that initially was headed up by Rich Margison. And ultimately, those branches went through many incarnations through various reorganizations, but through the period of right on through the 90s, Langley continued to maintain a very powerful CFD development capability and a very strong staff. Some of the leading people who came through the staff over the years included people like Craig Street, Jim Thomas, Ajay Kumar, Phil Drummond, and others who made major contributions to the development of CFD technology, particularly their practical application to aerodynamic flows. At iCase, we really had the who's who of leading numerical analysts of the 70s and 80s. iCase was originally headed up by Jim Ortega, who after a couple of years left Langley to go to UVA and become a department chair of mathematics there. And Milt Rose took over, who came to us from NYU, which was at the time sort of the leading institution in focusing on numerical solution of partial differential equations. And through NYU, we got hooked up with some of the leading folks like Tony Jameson, Ami Harton, Saul Barbanel, and many other leading scientists. Also at that time, Dennis Bushnell, who was a branch head, I don't remember exactly the name of his branch, but he brought to iCase a Dr. Yusuf Husseini, and Husseini built an extremely strong program at iCase in studying fluid dynamic turbulence and transition from laminar to turbulent flow. And some of the people who worked with Husseini in those years, like Tom Zhang, ultimately came onto the Langley staff. Others came and spent considerable time here, like Charles Speziali, and made significant contributions to understanding compressible turbulence and high-speed boundary layer transition. After Milt Rose became ill and had to retire, Bob Voigt, who had been the long deputy director of iCase, took over that institution. And then Bob ultimately left to go to William & Mary, first to the National Science Foundation, and then William & Mary, and Dr. Husseini took over the directorship of iCase until the late 90s, at which time he went to Florida State, and Manny Salas, who was one of the leading Langley CFD researchers, retired from NASA and took over the directorship of iCase. So those were some of the real leaders in the development of CFD at Langley, both at iCase and on the NASA staff.
During this period, what do you feel was the greatest challenge in facing CFD codes?
There were a number of interesting challenges. Clearly the biggest one, and it's still the biggest one, is fluid dynamic turbulence. Turbulence is still considered one of the great unsolved problems in physics. There's only a very sort of vague understanding of what it is, and certainly the details of what's going on in turbulent fluid flows are very, very poorly understood. But the phenomena comprise a broad range of length scales. And capturing that range of length scales in a numerical solution is a huge challenge. And in fact, the supercomputers of the day back in the 70s, 80s, and 90s were incapable of resolving all of the length scales. In fact, even today, the most powerful supercomputers can only resolve all those length scales for very simple elementary kinds of flows and very restricted physical conditions. So accounting for the effects of turbulence in the calculations was the biggest challenge. And it led to this whole field of turbulence modeling in which constitutive models were developed based heuristically, empirically, but not soundly theoretically. They led to complications in the form of the governing equations that are not mathematically well understood. In fact, my concern has always been that that we never really had a proof that there was a unique and well-posed solution, or a well-posed that the Navier-Stokes equations themselves, compressible Navier-Stokes equations themselves, represented a well-posed problem in a mathematical sense. There are proofs for incompressible Navier-Stokes and compressible Navier-Stokes under certain restrictions, but no general proof. And so my concern always was, when we sort of arbitrarily append to those equations these complex terms that account for turbulence, or actually additional differential equations, that we really had no clue as to whether we even had a well-posed problem. But beyond that, one was able to sort of tune up these turbulence models with experimental data, and as long as the calculation did not include physics that was far away from the physics in the experiments that you used to tune the model, you could do a pretty good job. But once you got away from that, the models were very inadequate, and we've never really been able to develop effective turbulence models to deal with things like highly separated flows, highly unsteady flows. That still remains a challenge in the field of CFD.
You eventually moved into position in the director's office at Langley. What was that position, and what were your duties?
Well, my first position in the Office of Director is I was the Associate Director for Research and Technology. And in that position, I had oversight over all of the technical organizations at Langley. And in that instantiation of our organization, they were referred to as competencies, but they were all of the aerospace, atmospheric science, and engineering competencies of Langley Research Center. Were organized into several large organizations that reported to me. I was the supervisor of the directors of those competencies, and had oversight of maintaining the capability of the center. That would be all of the facilities of Langley, as well as the intellectual capability of the center.
So you had some input into the direction that maybe perhaps research at the center took?
Yes, to some extent. I think during the period from the 80s to the 90s, NASA began the shift of technical leadership in the agency began to shift from center line management to program management. And in fact, in 1994, Langley reorganized itself into this matrix organization that still exists today. And so in the job as an associate director for R&T, my responsibility was for the line side of the matrix organization. So we were responsible for providing the talent and the facilities and laboratories required by the programs, and the programs established the technical requirements for the work.
Also, while you were the Associate Director, you served as Langley's representative to the Mars Program Independent Assessment Team. How did this team's findings impact robotic exploration on Mars?
The agency had launched two probes toward Mars. One was to be an orbiter, one was to be a lander, and both crashed on the surface of Mars. So this was kind of a major setback to the whole Mars program. And they, of course, each failure had its own accident investigation board, but the administrator also established this Mars Program Independent Assessment Team to take a larger systemic look at why we had these two failures occur literally within months of each other. And that team was headed up by Tom Young, who, of course, had his start here at Langley and was a part of the Viking team, but then had a career in industry, ultimately retired as a vice president of Lockheed Martin, and has been engaged in many investigations and advisory activities to NASA and the Department of Defense since his retirement from Lockheed Martin. So the team was established. There wasn't actually a center representative on these teams, but I was asked to participate on the team because of my knowledge of reentry and hypersonic aerodynamics, which is one of the issues associated with landing on Mars, is you have to fly through the Martian atmosphere. So I was invited to be on the team for that purpose. One of the major strategic decisions that Dan Golden made as administrator was this idea of the faster, better, cheaper mission. So he decried missions like the current Cassini mission, which he dubbed as Battlestar Galacticus. And in fact, at that time, the Cassini program, when Dan made the faster, better, cheaper decision, the Cassini was already under development. And his theory was that if you had a mission like Cassini that were multiple billions of dollars, took a decade to develop, and that if you had a failure on a mission like that, you lost essentially all your opportunity. So his idea was instead to have many cheaper missions. So if you lost a few of them along the way, you still had something out of the program. So these two missions that were lost at Mars were in this better, faster, cheaper category. The MPAT, as we called ourselves, discovered that this faster, better, cheaper concept was actually the root cause of the problem in these two failures. The faster, better, cheaper mantra led to project schedules and budgets that were unexecutable. So if you think about a project to put a spacecraft in orbit around Mars or on Mars or any other kind of a spacecraft, you have certain variables that as a project manager you can manage. You have your requirements, you have the money, you have the schedule, and you really need to, and you have risk. And you really need to manage those four things to meet the requirements as best as possible. What happened with the faster, better, cheaper is they tended to restrict the ability of a project manager to change requirements. That was really a Dan Golden thing. He didn't want to hear about it. To overrun budget or to overrun schedule. So when you're restricted in those three areas, what's happening is risk just goes where it goes. And in both of those missions, the risk went way, way up. There were not sufficient, the testing was insufficient on both missions, and it was because of that that risk went up. And it was really fascinating. In fact, one of the interesting things was on the lander that crashed, the Accident Investigation Board nor our team were able to come up with what happened. Had no idea why it failed. And part of the problem in not knowing why it failed was because of the faster, better, cheaper idea, there was no telemetry from that lander as it was, after it left the carrier spacecraft and went on to land at Mars. There was no telemetry, so there was no data, and the first data would come after it landed. So all we knew is we never got data. So the assumption was that it crashed, but didn't know really what happened to it. There was a follow-on mission, and when that spacecraft was being tested, they discovered a fundamental, it had the same lander leg system that the failed spacecraft had. When that lander leg system was undergoing testing, and they did more careful testing on the second follow-on mission than on the original, they discovered a logic flaw in the software that deployed the legs of the lander. And that logic flaw led the failed lander to think its legs were deployed when they were not. And so the thing hit the surface with legs undeployed, and that was it. I'm sorry. When the legs deployed, the retro rocket was supposed to fire, and the whole logic chain led to the thing landing without deployed legs. So in any event, it was really a very simple thing, and had the test been conducted properly, it would have been discovered. The tests were done hurriedly and not thoroughly. It was not discovered. We also found that when the software was developed, in order to stay within budget, software wasn't checked by an independent party. So it was the software error that led to the hardware problem, so we had failed software. So similar thing happened on the orbiter. It was a units problem, units conversion problem that led to the ultimate crash of the orbiter on the surface of Mars. The same sort of cutting corners at every step led to that failure, so we reported to that to the administrator. Now, Dan Golden was a very famous hot-tempered individual, so I went into the meeting that the whole team went into to hear, as Tom Young briefed Mr. Golden, and our fundamental conclusion was faster, better, cheaper was flawed. I was shocked to hear Mr. Golden accept that. And he admitted in that meeting that faster, better, cheaper could not work. And he said what he did not anticipate with faster, better, cheaper was what he termed the long green table, that Congress and the public do not allow NASA to fail. And so when we had mission failures, he would be called before the Congress, and he would be sitting at the witness table himself, answering the questions. That's what he called the long green table. And so he recognized that NASA had to have a far higher degree of mission assurance. In fact, he canceled the follow-on mission because of that, and essentially restructured the Mars program. In fact, the MPAT was asked to stay on a little longer and make recommendations as to how the Mars program should be restructured, and we made recommendations with regard to properly managing the four variables I mentioned earlier: risk, budget, schedule, and requirements. We made recommendations with regard to testing, test as you fly, fly as you test. An old mantra of the space program, to make sure that that remained a big part of how the program was managed. The other thing that Dan mentioned, which I thought was fascinating, was that he recognized that the capability in the aerospace industry to properly develop and manage these complex spacecraft no longer existed. And the only place that it remained was within NASA. That did not stop Dan Golden nor his successor, Sean O'Keefe, from continuing to destroy that technical capability within NASA, but he did admit that, which I thought was kind of interesting. So the meeting turned out to be less confrontational than I imagined it to be. Of course, Tom Young is a formidable person for Dan Golden to confront, but in any event, it was, I thought, actually a fairly productive report.
Subsequently to these failed missions, Langley had some roles in what we call entry, descent, and landing.
Yes.
And did CFD codes play a part in this?
Absolutely. Langley is really the center of excellence for planetary entry, descent, and landing in the world. Langley has been engaged in all missions that have successfully landed on Mars. From Viking, where we managed the whole mission, actually, and managed that entry, descent, and landing, or EDL as we call it, through all of the successful Mars landings since. Langley has not been involved in any of the failures to land on the surface, including, of course, the Russian failures as well as the American failures. So we have a strong core capability to predict the entry process that includes CFD, wind tunnel testing, trajectory analysis, parachute dynamics, all of the key elements of the EDL process we are able to simulate with a high degree of fidelity. And we also have developed over the years as good an understanding as there is of the composition and profiles, altitude profiles of the Martian atmosphere. And that's all rather key because just like Earth's atmosphere, Mars' atmosphere changes over time. So there are times when it's hotter, and of course around the planet. So depending on where you're landing, you have either more or less atmosphere to slow you down. Of course, the more dense the atmosphere is, the more heating you're going to get. So heating is also a major area of strength, aerothermodynamic heating of the center. So it is our combination of CFD, experimental aerodynamics, and trajectory analysis that allow us to have this strong capability in EDL. And now I think that's widely recognized, and we're engaged in the EDL of every mission. In fact, this last round of Mars Scout proposals that headquarters evaluated, Langley had the EDL role on every proposal. So I think the entire community now recognizes the importance of and the capability Langley has in this EDL area.
I have one final question. As Associate Director of Langley, what do you feel was your most significant decision or action?
I would say the invention and establishment of the National Institute of Aerospace. I mentioned earlier the key role that iCase played in CFD development at Langley. iCase ultimately spread its wings outward from CFD and had a strong role in nanotechnology and materials technology. It also, over the years, had been engaged in things like fault-tolerant software and formal methods, and computational structural analysis. So, iCase had done a lot of things and been a valuable resource for Langley. But as we went through the budget traumas of the late 90s and on into the early part of this decade, I recognized that there were certain limitations of iCase. First of all, iCase was a Langley captive. It was run for NASA by the University Space Research Association, commonly known as USRA, under a task order contract with Langley Research Center. But it was recognized as a Langley captive, and because of that was unable to get funding from other government agencies like NSF or DARPA or others, because everyone assumed, well, you know, Langley can fund that iCase work. So they had that limited capability, and I felt that we needed a strategic partner to help us gain more business from outside of NASA. Department of Defense, private sector, and so on. So I came up with this idea for the NIA as a entity independent, having some of the intellectual capability of iCase. In fact, ultimately, the model we developed, it had a stronger intellectual capability than iCase in the sense that we envisioned it having associated with it 6 faculty, full-time permanent faculty of the chaired professor caliber. But it was set up as ultimately by the winning proposer, a consortium of universities. It was set up as a independent 501c3 corporation that had a task order contract with NASA. It had a cooperative agreement with NASA, but was an independent corporation in the state of Virginia that could do business with anyone. And through its legal relationships with NASA, ultimately also a Space Act agreement, we could do work, Langley could do work for NIA, or NIA could do work for Langley. So that we were able to establish the NIA back in September 2002. First, we let the contract. It became operational in January of 2003. And in fact, it's right now going through its first renewal. The instruments, Kathy Kirk, who was our chief counsel at the time, and Kim Stone, our procurement officer, did some really creative work to establish a new kind of set of mechanisms to set the NIA up, including the task order contract that I mentioned, as well as the Space Act, or the cooperative agreement. But they were competed and awarded simultaneously. And it gave us a whole range of flexibilities with iCase that were unique in the agency at the time and recognized as a best practice by NASA headquarters at that time. So the NIA has turned out to be quite successful. We then ended iCase at the time that NIA stood up, and all of the tasks that were being funded through iCase were now transferred over to the NIA task order contract, and so they kind of took on NIA, or iCase, upon establishment, and in fact still maintain the iCase report series. I mean, there's no new iCase reports, but they maintain the availability of those reports because they had become world famous report series, and was really considered a very high honor to even publish an iCase report. So they maintain the intellectual heritage of iCase while developing their own new intellectual heritage and business base.
Some of the opportunities involved in the NIA include graduate students coming.
Yes.
And these graduate students are able to work on projects here at the center, or?
Yes. We embedded into NIA 4 capabilities. So the winning proposer would have to set up a structure that could work in all 4 of these areas. So the first area was leading edge research. Second area was education. The third area was technology transfer and commercialization, and the fourth area was outreach and public outreach. And NIA is engaged in all 4 of those areas today. So in the education area, there is a graduate program associated with the NIA. There are actually 7 universities that are a part of the consortium that operates NIA. The University of Maryland, Hampton University, University of Virginia, Virginia Tech, North Carolina A&T, NC State, and Georgia Tech. And then an 8th member of the board of directors is the AIAA Foundation, American Institute of Aeronautics Foundation. The provosts of each of those universities sit on the board of directors of NIA, and the president of AIAA Foundation sits on the board. So NIA is not a degree-granting entity, but students can matriculate at NIA and numerical solution of differential equations. And there was a strong program of visitors every summer. There would be 30 to 40 mathematicians and computer sciences visit through the iCase. And then during the course of the year, we would have faculty from around the world who would come in on their sabbaticals to work with our staff. So that program continued for a good 20 years, and through it, many of the advances in computational fluid dynamics, especially those associated with compressible flow, were developed. So for example, we had visitors from Israel and Europe that helped us develop a class of numerical algorithms known as total variation diminishing methods that were attuned to capturing shock waves without excessive oscillations in their immediate vicinity in the computation. We worked a lot to try to understand on the center at that time called iCase. Had the original name of the Institute for Computer Applications in Science and Engineering, ultimately just officially shortened its name to iCase because it was widely known by that acronym. That institute was established by Dr. John Duberg in 1972 when he was the then associate director of Langley Research Center, and he established it to take advantage of a unique opportunity at Langley, which was the acquisition of an early supercomputer called the Star 100. This was a vector supercomputer, the first of its kind. It was put on the market by Controlled Data Corporation, which now doesn't even exist anymore. So he wanted to provide a place where we could invite mathematicians and computer scientists to come work at Langley with our staff to take advantage of this new computer. So through iCase, Langley established a vibrant program of visitors in the fields of computer science and mathematics, particularly the mathematics of
This is Gail Langevin with the Office of Strategic Communication and Education. Today is March 30th, 2007, and I'm speaking with Doug Dwoyer, Associate Director of Langley Research Center. Doug, when you began at NASA, what branch were you assigned to and what were your duties?
I was assigned to the Theoretical Aerodynamics branch. Jerry South was the branch head, and my duties were to develop computational fluid dynamics techniques for predicting transonic aerodynamics.
And tell me more about the development of computational fluid dynamics, or CFD codes.
Well, when I joined NASA in 1977, the name computational fluid dynamics, or CFD, had actually just begun to be used. It was before that, a number of people were experimenting with using numerical solutions of differential equations to predict fluid flows in academia, solving the true nonlinear equations of fluid mechanics first, remaining with the approximation of inviscid or ignoring viscosity in the calculation for the majority of the flow, and then accounting for viscosity with boundary layer calculations. And then on into the 1990s, focus again began to shift to solving the full equations as they were known at the time of fluid mechanics, which are the Navier-Stokes equations, but amended to account for the effects of fluid mechanical turbulence in an approximate way as opposed to an exact way. So there was added to the Navier-Stokes equations the so-called turbulence models. So Langley, one of the key roles that developed at Langley was around the mathematics of the solution of all of these classes of equations, the linear equations, the nonlinear inviscid, and ultimately the Navier-Stokes equations. And a rather innovative way that Langley was able to do that was through an institute that was in various government labs, but it was not really an organized discipline. And in the 1970s, it began to emerge as an organized discipline in mathematics and engineering. And Langley and NASA played a major role over the next 30 years in the maturation of CFD, particularly in its application for aerospace engineering. At the time that I joined NASA, most CFD techniques were focused on the numerical solution of linearized equations of motion for aerodynamics. These are approximate equations of motion that ignore certain key features of aerodynamic flows. For example, in a linearized model, you cannot predict shock waves. And then they were accompanied by numerical solutions of the boundary layer equations. As we went into the 1980s and the late 1970s, really, the focus began to shift to solve